Okay, now let's find out how the Maxwell's equations look like in differential form. So let us start with Maxwell's first equation. Now in the integral form, the first equation looked like this, which tells us that the electric flux through a closed surface S is equal to the total charge inside that closed surface Q divided by epsilon naught. Now from the Gauss's theorem, we know that this flux can be written as the volume integral of the divergence of electric field. Now to write down the right hand side as also a volume integral, we can replace the total charge as the volume integral of charge density. So we get this equation as a result. And notice that here this volume is not limited to any type of volume. It is valid for any volume including an infinitesimal one. And in that case, we can write down the integrands of these two volume integrals to be equal. That is, the divergence of the electric field is equal to charge density by epsilon naught. So this is the first Maxwell equation in differential form. Now the second equation of Maxwell tells us that there is no magnetic monopole. That is, the total magnetic flux through a closed surface is equal to 0. Now applying Gauss's theorem, we can rewrite this surface integral as the volume integral of divergence of magnetic field, which is valid for any arbitrary volume V. And now for this integral to be 0 for any arbitrary volume, the integrand here must be 0. So it implies that the divergence of magnetic field is equal to 0. And this is Maxwell's second equation in differential form. Now let's turn to Maxwell's third equation. The integral form of Maxwell's third equation tells us that the electromotive force induced in a loop, which is equal to the line integral of electric field over that loop, is equal to minus the rate of change of magnetic flux through the surface of that loop. Now applying Stokes' theorem, this line integral can be written as the surface integral of the component of curl of electric field normal to the area of the loop. And in the case of a stationary surface, we can pull this differential operator inside. Now this equation is valid for any arbitrary surface. So the integrands of these two surface integrals should be equal. That means the curl of electric field E is equal to minus the rate of change of magnetic field with time. And this is the differential form of Maxwell's third equation. So now, this is the fourth Maxwell's equation in integral form, where this is the displacement current and this is current density J. Now by applying Stokes' theorem, we can write down this line integral as the surface integral of the component of curl of magnetic field B perpendicular to this area of the loop. And if the surface is stationary, then we can pull this time derivative inside the integral to act on this. So we get this. Now, as this expression is valid for any arbitrary surface S, we can write the integrands of the both sides to be equal, which gives us this equation, where the curl of magnetic field B is equal to mu naught times current density J plus epsilon naught mu naught times the time rate of change of electric field E. And this is Maxwell's fourth equation in differential form.